Okay, so today I'd like to talk about the automatic speech recognition. This is one of the most active research area in speech processing, and also very important application for multilingual NLP. And today I will first explain about the speech recognition demonstration, and also talking about evaluation metrics. And I will little bit use the math to explain about the formulation of the speech recognition, and we'll move to the explanation about the standard speech recognition pipeline. So let me first try to work on the demonstration, which I just try to kind of use speech recognition here. I want to go to the CMU campus. Perfect, right? That's the technology. And I also want to show how the current ASR technology is robust. I want to go to the CMU campus. Oh, it doesn't work. Next, maybe I can speak slowly. I want to go to the CMU campus. That's the current technology. Next, I mentioned that the speech recognition is not good for the noisy environment. So let's try to make the noisy environment. I want to go to the CMU campus. They are cool, right? Yeah, they are very, very cool. So I tried to kind of make some kind of a mistake, but the Google guys are doing a great job. So it's actually not easy to find some kind of a significant mistake with them. One of the easy mistake that I can that try to make could be the other query. My name is Shinji Watanabe. Okay, right? Yeah. They should, study more about me. I will talk to my colleagues in Google. And the other difficulty would be, let me try. So I mentioned that the speech recognition is not very good under the simple noise. It's actually quite strong. But if there's some the other speakers are speaking, it's still very challenging. So I try to make this kind of situation.
So do you have a long? I guess not if there's. I was raised in New York, but I guess up there y'all don't have too long of a growing season.
I want to go to the CMU campus. Sorry.
Do you do your own gardening?
I want to go to the CMU campus. They are not bad this time, but it's actually not working quite well in general. So these are current technology with some more, how do I say, with a controlled environment. The speech recognition is quite working well. And today's talk, I will talk about introduce about the speech recognition technology inside. Okay, so the first example I already mentioned. This is one of the mistake that I found when I use the Siri, and yeah, sometimes very good, but sometimes it's not working. And what kind of errors the speech recognition has will be today's discussion. So please discuss it in the rest of the class after my lecture. And now the many of the speech recognition engines actually also support the other languages. And I also tried the Japanese, and it's working quite well. I tried several times, and then I found this kind of mistake. But in general, other language also working quite well now. And now I will move to the evaluation. As you can see, sometimes it's perfectly working, but sometimes it's not working, right? And then the how to evaluate the measure in speech recognition is quite important. And the first, the most intuitive measure would be the sentence level error. Anyway, the sentence is correct or not. I think it is the most the important measure, I would say. However, by measuring the performance of the system, in this case, it's almost correct, right? It's just there are a few words are the wrong. So we actually want to give some partial score if the half of the words are correct. So to do that, instead of using the sentence error rate, we usually use the word error rate. And the word error rate is computed by considering the three types of the error. One is the insertion errors. In this case, this word is actually the extra word compared from the difference. So this the word error corresponds to the insertion error, and then the rest of the error is correspond to the substitution errors. By the way, it is not unique. Of course, we can consider this substitution. This one is a substitution, and this one the other insertion, and so on. And usually we consider all the possible the error, and then taking the minimum by also considering each cost of each error, and then compute the edit distance. I think many people here would be familiar with the edit distance, so I may not need to explain about it in so much detail. But anyway, this is our kind of a usual the measure to check the performance of the speech recognition. And so this is a quite well defined measure when we have a word boundary. But as you can see, we have a lot of the languages which actually don't have a word boundary, right? And how to compute it? There are two ways. One is just using some tools to segment to get the kind of word you need, and then the computing the word error rate. But we should be very careful about that because this chunking may depend on the tool or dictionary and so on. I had a very bad experience that I compared my Japanese system and other the institute the systems, and ours are actually quite bad, and I was very disappointed. But I couldn't reach to their numbers, and finally we asked them how to chunk their word, and their tools are different from ours, and then we actually cannot compare, right? So it is the issue when we using the chunking, but still if we use the same chunking, we can compare. So this is widely used, but the mostly used the metric for such kind of languages is actually character error rate. Just consider the each character and the computer edit distance. So this is the more widely used when the computer measure for the languages that doesn't have a word boundary. So the assignment 3, the first you guys pick the language, right, and then do the ASR and do the evaluation. Be careful about the which measure are you guys using. If that language has a good word boundary, you guys can use word error rate, but otherwise character error rate is safe. Yes.
When you're speaking in Japanese, do you expect the system to transcribe the word CMU in Roman?
Yes, actually yes. Yeah. Since it's a kind of the already the training data and so on mixed. So it's the appeared as the Roman character in the Japanese cases. Yeah. Japanese cases, we have a tons of data. So actually this kind of mixture will be handled by data-driven manner. However, I think in some sense you're right. For example, this CMU, which can be also written as the katakana the script, which is the other the Japanese script to describe the word from the foreign countries. And this may also happen. CMU katakana instead of this kind of Roman character happens. And then in this case, the word error rate or character error rate, both cases, it was correct, but it was regarded as a wrong mistake. So actually, in this sense, it depends on the language, but in some languages, the same the word can be represented as a different script. And then the word error rate or even character error rate is not a perfect measure. But this is a very difficult problem, and usually we normalize to either of the symbols, or we actually don't care so much about that. And there are a lot of other metrics. Since the script has an issue, like as I mentioned, some people use a phoneme error rate, but this actually loses the semantic the information a lot. So this is used to check whether this speech is acoustically, phonemically correct, but it's not sure it is semantically correct. So it's not so much used. But anyway, this is also another measure. Frame error rate is also sometimes used, but I skip the explanation. And the other metrics, recently these two the metrics are quite important. Real-time factor and the latency. Since many of the systems are now in on the device and so on, and the speech is used as an interface. By the way, speech has another application, the offline archive and so on. We don't care about the at least latency. Real-time factor, the smaller, maybe better, but the latency is quite important if you're using a speech interface. And it's also depend on the downstream evaluation metrics. For example, if we combine this one with the understanding system, or if we combine it with the translation system, of course we should evaluate it with such kind of a downstream the evaluation metric. So in the speech translation cases, of course it can be better if speech recognition performance is better, but we just check the blue. And for speech recognition, especially the character error rate or word error rate, I recommend you to use the NIST speech recognition scoring toolkit. How many people know NIST? NIST is the government institute to standardize our the daily life activities, including for example, the atomic clock, the unit of the time. That was also the standardized by the NIST, and the NIST is actually helping us, our community, to standardize such kind of evaluation metric in speech and NLP processing. So, and then of course, if we use a different evaluation tools measures, and then if this kind of result is different, we cannot compare your result with others, right? So due to this reason, I actually recommend you to use the SCTK or other standard, the standardized or the widely used the error evaluation metric than some tools that someone just made it to avoid to have some the confusions. Again, if the evaluation metric tools are different, it is disaster, right? Okay, so with this kind of a great help from the NIST and so on, the speech recognition actually was well measured in terms of the word error rate or the character error rate. So everyone can, for example, compare the performance. The others are difficult, right? And in the previous lectures, Graham also discussed about the blue or other evaluation metrics in machine translation. And there are some discussions whether which one is better or not. Word error rate, character error rate, there's not so much discussion. Mostly it's correct, I would say. There are some kind of exceptions that I mentioned before, but it's mostly correct. And also, nice part is that this has a very high correlation with the downstream tasks. Better word error rate, definitely better in the speech translation, right? So anyway, due to that, and also the NIST are providing such kind of toolkit so that everyone can compare the error rate strictly. So this is the one reason that the speech recognition has been studied for a long time with a common benchmark. So now that every field, we have the common benchmark, and then performance measure and the leaderboard and so on, right? Speech recognition actually has a long history of the comparing the techniques based on the shared the data, the same the evaluation metric. And this is a kind of the figure that I often show in this lecture. This is a switchboard task. And as I mentioned, everyone since 1990s up to now, 20 to 30 years, we're still using this data, and we're still using the same evaluation metric so that we can track the performance, the improvement. So this is possibly the one reason that actually deep learning has been applied to many areas, but the speech is actually one of the first areas that deep learning is applied. Since we can easily also fairly show the performance improvement based on this the evaluation measure. Okay, so yes, the card.
Graph is interesting from 2000 to 2002. What are they increased?
This area, right? By the way, this area is the what when I started speech recognition. This area is one of the cold error. So any techniques that cannot improve the performance, we also cannot the further the scale, the training data, and so on, and also the budget, big project, the kind of the decreased in this era for speech recognition. Anyway, this is the kind of one of the cold age in speech recognition. It's some slight improvement happens like a discriminative training and so on. But before deep learning, and this I would say my most kind of speech recognition history, by the way. But when I went to the conference, we always talking about the method A get a 0.3% moderate improvement. Wow, that's a very good technique. Only 0.3 or something like that. Yeah, but due to the deep learning, such kind of the how to say, we saw that this is shrinks and cannot reach to the human performance, but thanks to the deep learning and the computational, the breakthrough GPU, and so on, and also the open source or other people's the knowledge sharing, now makes the performance to be improved better and better. Okay, so by the way, one more thing. Some people say speech recognition research is easy. This is because we have a evaluation metric. So the other areas, it's not easy because we have to start to make an evaluation metric by ourselves, or there's multiple evaluation metric and we have to pick or something like that. So instead, speech recognition is actually regarded as an easy research topic in terms of that we have a fixed evaluation metric. So if you guys have a fancy neural network and then get the improvement by 1%, you can write a paper. Okay, so I will move to the speech recognition. I need to kind of swap that. A little bit using a mathematical formulation of speech recognition. So first, speech recognition, as I mentioned in the several times, is quite interesting conversion problem. Input is completely physical signal, wave pressure, sound pressure, right? That goes to the linguistic symbol. So physical one becomes the linguistic symbol. It's very different, right? And the input, the characteristics is also very different. The waveform is just the one sentence. It can be like a 2 to 3 seconds. And if with a kind of the 16 kilohertz sampling rate, the length will be the order of 10,000. If we use a short-term Fourier transform and other speech features, it goes to the 100 order, but still a bit wrong, 100 to 1,000. That only goes to the 3 lengths of the symbols. So the word in the vocabulary. So this the conversion from input and output is I would say quite different, and this actually makes the problem quite difficult. Okay, so now I try to kind of explain how the speech recognition is realized one by one. So the Google the demonstration, you guys just see that it is one box, right? But it's actually inside there are several boxes. First one is the feature extraction. This is, I think I don't have to mention about so much about it. Any of the pattern recognition machine learning problem, we first have the feature extraction, right? And in speech, anyway, waveform is not easy to deal with. So instead, we're using the feature extraction called MSCC. I have 2 more slides explaining this each of the modules. So I will explain a bit more detail about it. But anyway, from now on, I will start from the feature, which is continuous vector, time series of the continuous vector, and then the mapping to the word sequence. How to formulate it? One way is we just ad hocly making it as a regression problem. But instead, the people actually formulate this problem more mathematically rigorous ways. They started to formulate this problem as a map decision theory. Here, the posterior is this one, PW given no. So the posterior probability of the word sequence given the observation. And then among all the kind of word sequence, we just try to pick up the most likely sequence. That becomes a speech recognition. Quite simple, right? And the problem issue is how to obtain this PW given no. So this is the kind of the speech recognition problem that we usually use for the probabilistic formulation. And there's a couple of the rules that we usually use. If I have time, I will explain a bit more carefully about this one. But anyway, I just want to mention that why people using a probabilistic formulation. There are a lot of reasons, but one of the reasons is that we don't actually have to remember various kind of equations. We just have a 3 equations: product rule, sum rule, conditional independence assumption. Conditional independence assumption is that rule, but maybe just include in this lecture as a rule. But by only using these 3 basic probabilistic rules, we can actually make this PW given no problem a bit more tractable. So the first thing that people may often see for the speech recognition is to use base rule to change this PW given O to PO given W, PW divided by PO. And then since the PO is not depending on the W, we actually use the PO given W and the W. So to derive this one, which rule did we use? From here to here mainly. Yeah, product rule, yes. So by using the product rule, we kind of changing the problem from the original posterior distribution to the likelihood and the prior distribution. This is the methodology is called the noisy channel model, and the people are actually using this method. But is that enough to solve the problem? For me, it doesn't actually change the difficulty, or even looks like it's more difficult, right? And then the how to make this problem more tractable, we actually using the additional information. So speech to text, anyway, this is a very different the conversion. We want to have something between. What layer we can introduce? Like our linguistic knowledge, we can use phoneme, right? And then this is a little bit easier, right? From O to directly predicting the word is kind of difficult, but by using the phoneme intermediate representation, each kind of a conversion is a bit some problem, and this is easier. So this kind of methodology is quite important to solve the very difficult conversion problem. Okay, so now we have a phoneme sequence. Let's use the phoneme sequence. How to introduce this phoneme sequence in this the probability distribution? Some people may answer if they took my course in the speech recognition and understanding. Which one we use? Sum rule, product rule, conditional independence assumption. It's actually sum rule, right? Sum rule is great. We actually can introduce the additional variable, right? Still, this doesn't change anything. Doesn't change the difficulty. So how to further change this problem? We just using the product rule, like I mentioned before. It's part of the base rule, but by using the product rule, we can further factorize this problem to the 3 distribution. And one distribution in the denominator, but this is not related to our the optimization problem, so we can safely actually ignore it, right? Is that everything? It's actually not. This is just equivalent the conversion, right? It actually doesn't change the difficulty. How to make the problem more simple? We're using the conditional independence assumption. For these cases, where we use a conditional independence assumption, here. These are reasonable assumption, right? The relationship of the observation, speech features, only depend on the lexicon, through the lexicon, phoneme, than the word. It's a little bit approximation, but it's reasonable, I would say, right? So we actually using this conditional independence assumption everywhere to make the problem tractable. For example, the acoustic model, we further apply the conditional independence assumption. Hill-Markov model is one of the conditional independence assumptions to make it tractable. And we use an n-gram language model. Now we use a neural language model, which actually doesn't have that, but they used to use the n-gram language model. This is also conditional independence assumption. So by using that, we actually making this problem tractable. And this methodology is quite powerful, actually. It's not only used for speech recognition, by the way. This is also used for the machine translation as well, before neural machine translation comes. So actually the IBM is the same the group, same division propose both speech recognition and the machine translation in this kind of a statistical form. Okay, so now I decompose this the problem to the 3 distribution, right? This is actually structure that we solving the speech recognition. So the first part, feature extraction, again, this is not included in the probabilistic the representation. The first one is acoustic modeling, lexicon, language model. It sounds like we just combined some kind of the sub-problem, right? But it's actually mathematically well decomposed. And then we make each of the sub-problem tractable. And then finally combine it based on the equation. This is the math of the speech recognition. Or other the problem of solving the sequence to sequence model before neural model comes. So the important concept is factorization to make the kind of problem to be decomposed. And the other is factorization itself doesn't change the difficulty. We also have to have a conditional independence assumption to make the problem tractable. So I don't know how you guys feel. When I first learned this one, I thought that this is very elegant. The first, I just learned speech recognition is these 4 components. Oh my God, it's just complicated. The some modules are combined to make a speech recognition. Sounds like very cool, but a bit less theory. But it turns out that it has a quite beautiful theory. To the original target is the Bayes decision theory, and introduced each of the submodule based on the probabilistic formulation. And actually, in the following the slide, I will talk about each of the module a little bit more. But usually, I skip the details. And if you guys want to know more about each of the module and so on, please also consider to take speech recognition and understanding courses in the fall semester. Okay, maybe I can accept one of few questions here. If not, I can move to the each of the pipeline quickly. The first part, feature extraction. this is before goes to the probabilistic model. The feature extraction, we use the signal processing techniques to convert the waveform to the mel frequency capture coefficient (MSCC) or other features. And I just want to link the multilingual NLP. This process is mostly the language independent process, as you can imagine, right? This is just a signal processing to convert the waveform to more tractable the feature. So this is actually the result of the conversion from the waveform to the MSCC. I think most of people could agree the bottom figures have more patterns, right? And more patterns. So this is very important to make the feature to be used for the backend the processing. By the way, this signal processing based approach is gradually replaced by the deep learning. This is also happening now. So one is people using actually the CNN instead of MSCC, or some other people also using a self-supervised learning now. This is very powerful. But the drawback is that this is a learnable, learning-based approaches. So then the probably language independence property will be kind of mitigated to do that. Next, acoustic modeling, which converting the speech features to the phoneme the sequence. And for this, the acoustic modeling, we using the combination of the hidden Markov model with Gaussian mixture model or deep neural network. And this approach is also the mostly language independent because speech features are more like language independent. And the phoneme is also, if we design well, it can be a language independent, or at least not so much. We can make it not so much depend on the languages, although it is actually a bit difficult. Okay, so the hidden Markov model is the actually quite important part in this the modeling. What hidden Markov model is doing is actually the quite important role in the entire speech recognition. So as I mentioned, the speech recognition, the one of the difficulty is the output, the symbol, and the input, the lengths are very different. So we need to make some alignment of the speech features and corresponding to the phoneme the information. So in this case, we don't know which boundary we should take for the each of the phoneme. And to do this kind of alignment problem, we classically using the hidden Markov model. And the hidden Markov model is more like a charging of this, making this kind of alignment. And given this alignment to provide the accurate likelihood based on the Gaussian, used to be Gaussian, but now deep neural network. That is a kind of acoustic model. And by the way, this acoustic model part is the most important to get the performance than the other components in general. The third module is the phoneme to lexicon, phoneme to word conversion, and we use the pronunciation lexicon, made by the expert linguist and so on. And this part is heavily language dependent. So to do that, we actually need to first access to get the dictionary information. And I actually usually show you the CMU dictionary. This is one of the most well-known English dictionary maintained by here. But unfortunately, it's the server is down now, so I cannot make a demonstration and so on. But this CMU dictionary, the English is very lucky because we have a CMU dictionary, and then we can build a speech recognition system. The other languages, it's actually not easy to get that. We don't have so much kind of structured and the accessible dictionary in the other languages. However, probably I use this Wiktionary, and if using the Wiktionary, we can also somehow get to the information about the phoneme. It's actually covered many languages like this. By the way, I also, it's not recovered yet. Not yet. Okay, this is unfortunate. So, okay. So by using that, we can also use make a kind of this lexicon component for each languages. And the last part is the language model. And the language model that we use an n-gram or recurrent neural network. And usually, what language model will be built is that we try to kind of get the how possibly that word given the pronunciation we can have given the kind of the word sequence how possibly we select each language depending on the context. That is what language model is doing. And this the example, I actually have these three word sequence. This is, by the way, the same go-to in terms of the phoneme. And it can be actually go-to or go-to or go-to, right? And then if, for example, if we check this Wall Street Journal sentences and check whether how many times this pattern appeared, and then we can get the how likely this the phrase appeared, right? Go to appeared 51 times, but the others actually do not appear. So this means that this go to will be most likely selected based on the language model, right? However, this actually also has some kind of the issues. Actually, this pattern still exists in our languages. So I actually include the text size from the 10,000 order to the million order, and then count go to still the biggest, more than 2,000. Can you guess how many times go to appears in the Wall Street Journal sentences? 2 times, only 2 times. This is one example. It's not completely good sentence, but yeah, it appears, right? And the go to, how many you guys can guess? It's actually quite a large number. And yeah, most cases go too far. This is the sentence that often I saw when I search this two phrases. So if we're using the small corpus, it doesn't cover. But if we're using the large corpus, we can cover it. So this is the kind of power of if we're using a large corpus, we can cover many of the various the language pattern as much as possible. And this part is also language dependent. So this is the most building block of the speech recognition. And actually, I would say that it is not easy to build that for you guys. Each of the components is governed by the different model: feature extraction, signal processing model, acoustic model, the pattern recognition, machine learning, deep learning, and so on. Lexicon more like coming from the computational linguistic or linguistics. Language modeling is also comes from the NLP or the now deep learning. But anyway, each of the modules has a different models. So it is very difficult to actually develop all of them. And also connecting all of these kind of modules is also not easy. So instead, now people are also working on the end-to-end speech recognition. which try to make entire pipeline as a single neural network. Google's demonstration, it's actually they already switched to the end-to-end neural network. Other companies, as far as I know, they still didn't switch to the neural network, end-to-end neural network, but by using this pipeline. And so maybe, yeah, maybe that's it. I want to finish my talk. So this is a summary of the speech recognition. First, speech recognition is very well-defined problem. And also, fortunately, we have a large corpus. So it is quite often used as the measure for our new machine learning algorithm. And the factorization and making the problem tractable, this is a kind of great methodology for us to tackle this problem. And since this methodology is a bit complicated, recently people are also interested in and actually having a lot of development in the end-to-end speech recognition, which will be covered in my next lecture. And then this is the main topic, the assignment 3. So please enjoy the speech recognition. And let's move to the discussion. I think you guys already tried speech recognition engine by yourself, right? And then talk about what kind of errors you happened, and also apply to the other language and discuss about it. And since we don't have enough time, we don't have the final discussion time. Just split and then discuss it and then finish it. Okay, so let's split it.